What problem does the proposed method aim to solve in the context of large language models, LLMs?
The proposed method aims to solve the problem of adversarial attacks on large language models, LLMs. Specifically, it addresses the issue of jailbreaking attacks, where an attacker crafts adversarial prompts to manipulate the LLM into generating harmful or inappropriate responses. The method focuses on generating diverse, human-readable adversarial prompts that can bypass safety mechanisms and exploit vulnerabilities in the LLM. By training an AdvPrompter model to efficiently generate such prompts, the goal is to enhance the robustness of the LLM against adversarial attacks, ultimately improving the safety and reliability of the model's responses. The method aims to proactively identify and fix vulnerabilities in LLMs to ensure their safety and alignment with positive societal values, mitigating the risks associated with toxic content and inappropriate responses generated by the models.
How does the proposed method AdvPrompter work, and how does it generate diverse human-readable adversarial prompts? Illustrate step by step.
The proposed method, AdvPrompter, works by training another large language model, LLM, to generate adversarial suffixes against a target LLM. The training process, called AdvPrompter train, alternates between two steps: AdvPrompter opt, which efficiently generates adversarial suffixes that jailbreak the target LLM while maintaining human readability, and supervised fine-tuning of AdvPrompter using the generated adversarial suffixes as targets. AdvPrompter generates diverse human-readable adversarial prompts by conditioning the suffixes on the instruction, even when generalizing to previously unseen test instructions. This adaptability to input allows AdvPrompter to generate natural-looking adversarial suffixes that blend well with the context. Once trained, AdvPrompter can rapidly generate adversarial suffixes simply through next token prediction, unlike previous methods that require solving an entirely new optimization problem for each generated suffix. Additionally, AdvPrompter train does not use any back-propagated gradient information from the target LLM, making it faster and more memory efficient compared to previous works. This method offers efficient adversarial training for improving the robustness of LLM alignment by generating diverse human-readable adversarial prompts that mimic human-written prompts.
What are the key advantages of using AdvPrompter compared to existing methods for generating adversarial prompts?
The key advantages of using AdvPrompter compared to existing methods for generating adversarial prompts are: 1. Human readability. AdvPrompter generates coherent human-readable adversarial prompts that mimic human-written prompts, enhancing the effectiveness of the attack while blending in naturally with the context. This human mimicry behavior is induced naturally during training without human guidance, unlike other methods that may require human annotations. 2. Adaptivity to input. The suffixes generated by AdvPrompter are conditioned on the instruction, even when generalizing to previously unseen test instructions. This adaptability allows for more natural-looking adversarial suffixes that are tailored to the specific instruction, improving the success rate of the attack. 3. Fast generation. Once trained, AdvPrompter can rapidly generate adversarial suffixes simply through next token prediction, significantly reducing the time required for generating attacks compared to previous methods. This efficiency enables efficient, multi-shot attacks and scales favorably with dataset size. 4. No gradient from target LLM. The training procedure of AdvPrompter does not rely on back-propagated gradient information from the target LLM, making it faster, more memory efficient, and allowing for direct training against graybox target LLMs. This approach simplifies the training process and enhances the model's efficiency. 5. Efficient adversarial training. AdvPrompter enables efficient adversarial training for improving the robustness of LLM alignment. By generating diverse human-readable adversarial prompts, it provides a scalable and effective method for enhancing model robustness against adversarial attacks. 6. Amortized optimization. AdvPrompter's training approach is an instance of amortized optimization, where the cost of solving optimization problems during training is amortized, making it more efficient to generate new adversarial prompts from the same distribution. 7. Scalability and effectiveness. AdvPrompter outperforms existing methods in terms of OSR and perplexity scores, demonstrating its scalability and effectiveness in generating successful adversarial prompts while maintaining human readability. 8. Automated end-to-end process. AdvPrompter automates the entire process of generating adversarial prompts end-to-end, targeting specific harmful instructions without the need for manual intervention or dataset compilation, making it a comprehensive and efficient solution for adversarial attacks on LLMs. 9. Enhanced performance over time. While initially, AdvPrompter may produce lower quality suffixes, as it gets trained, it learns to predict more promising candidates with high probability, leading to continuous improvement in the quality of generated suffixes, surpassing the quality of prompts generated by other methods. 10. Adaptability and diversity. AdvPrompter's adaptability to unseen instructions and the diversity in the generated adversarial prompts contribute to its success in attacking LLMs, making it a versatile and effective tool for generating adversarial prompts.
How is the method validated or tested in the paper?
The method is validated or tested in the paper through a series of experiments and evaluations. The paper utilizes the AdvBench dataset, which includes harmful instructions and desired positive responses, divided into train, validation, and test sets. The method is tested in both white box and black box settings using various target LLMs, such as Vicuña 7b, Vicuña 13b, Falcon 7b, Mistral 7b, Pythia 12b, GPT-3, 5, and GPT-4. The primary metric used for evaluation is the attack success rate, OSR at K, which measures the success of generating adversarial prompts to elicit desired responses from the target LLMs. The paper also employs keyword matching and LLM-based evaluators to determine the success of the attacks. Additionally, the method is tested for robustness by fine-tuning the target LLMs with synthetic data generated by the AdvPrompter and evaluating the OSR before and after fine-tuning. Ablation studies are conducted to analyze the impact of different parameters and sampling mechanisms on the performance of the method. The paper also compares the method against baselines like GCG and AutoDAN to showcase its effectiveness. Overall, the method is rigorously tested through various experiments, evaluations, and comparisons to demonstrate its efficacy in generating human-readable adversarial prompts and improving the robustness of LLM alignment.
What specific results were achieved with AdvPrompter in terms of attack success rate and efficiency compared to baseline methods?
The specific results achieved with AdvPrompter in terms of attack success rate and efficiency compared to baseline methods are as follows. AdvPrompter outperformed baseline methods in both white box and black box settings, demonstrating higher attack success rates, OSR, with low perplexity scores. In the white box setting, AdvPrompter achieved higher OSR at 1 and OSR at 1.0 compared to GCG and AutoDAN, with significantly improved performance with OSR at 1.0. AdvPrompter also showed faster generation of adversarial prompts, generating a single adversarial prompt within 1 to 2 seconds, while previous methods took 20 minutes to several hours. In the transfer attack setting, AdvPrompter consistently outperformed baselines across all target LLMs, especially excelling with OSR at 1.0. Additionally, AdvPrompter demonstrated the ability to enhance model robustness through adversarial fine-tuning, reducing OSR and increasing model resilience against jailbreaking attacks. Overall, AdvPrompter proved to be more effective, efficient, and adaptable in generating diverse human-readable adversarial prompts compared to GCG, AutoDAN, and other baseline methods.
What are the limitations or drawbacks of using AdvPrompter in the context of adversarial attacks on LLMs?
The limitations or drawbacks of using AdvPrompter in the context of adversarial attacks on LLMs include the fact that the generated adversarial prompts may initially have lower quality compared to other methods, such as AutoDAN, in terms of the regularized adversarial loss. Additionally, the performance of AdvPrompter relies on the training process, and it may take time for the model to learn to predict more promising candidates with high probability. Another limitation is that the success of the attack heavily depends on the adaptability and diversity of the adversarial prompts generated by AdvPrompter. Furthermore, the computational cost difference between evaluating OSER at 1 and OSER at 1.0 is negligible for AdvPrompter, but it adds a factor of 10 for other baselines, making multi-shot attacks impractical for them. Lastly, while AdvPrompter offers efficient and scalable synthetic data generation for safety fine-tuning, further research is needed to explore the potential for fully automated safety fine-tuning based on joint training of AdvPrompter and the target LLM via self-play.